Good day, grade 10s. Today we are going to look at a September paper 2025, which is a preparatory exam. Right, our duration is 2 hours and marks is 100 marks there. Okay, so those are the instructions. Then we're actually going to proceed to question number one, which reads there, which one of the following is a molar mass of carbon dioxide, right? So we're looking for the molar mass of carbon dioxide. So if we're to look at the molar mass of carbon dioxide, we are supposed to go have a formula for carbon dioxide first, right? So it means our carbon dioxide there by formula is CO2, right? So it means the molar mass of this one is going to be in bracket there. We are going to look at carbon first there, bracket there, carbon then. Let's go to our periodic table where we're actually going to find our carbon. So it's going to be carbon 12 there. You can see our carbon is carbon 12. Therefore, we're going to say 12 multiplied by 1, then in brackets, say plus again. We move on to oxygen. Our oxygen there has got a relative atomic mass of 16. Therefore, we're going to say 16 multiplied by 1. Then we're actually going to get a value of what? 12 plus 16, which is equivalent to 44 there. So our answer is going to be 44. So our final answer there, correct option is going to be option B, which is 44 grams per what? Per mole, like that. Then to proceed to question 1.2, 1.2 reads, which one of the following, which one is of the following is correct? So we're looking for a correct option, right? So we're given here distance, displacement, and speed. So it seems here we're supposed to identify them as being what are scalars and vector quantities, right? So here I will automatically select my speed and say this one is a scalar quantity. Then the next one is my displacement, which is a vector quantity. Then the final one is distance also, which is a scalar quantity. So these are the top options that we are looking for there. So let's look the one that is a scalar there. Option A agrees with distance, it disagrees with what displacement, therefore it's incorrect. So A has failed the test there. Then B is a scalar quantity, then vector, displacement is a vector, and then speed is also a scalar. Therefore, our correct option there is going to be answer B. Then all these are actually going to be wrong because distance is not a vector quantity, it's a scalar quantity, while it's also displacement is a vector, not a scalar quantity. Speed is also what? A scalar, not a vector. Then there's no need for me to look at option D. The correct answer there is going to be our option B. Then we proceed to 1.3. 1.3 reads, two forces of 3 newtons and 12 newtons act at a point on the same flat plane. Which one of the following is a possible value of the resultant, right? So resultant, by definition there, we know a resultant is a single vector having the same effect. So it's a single vector having the same effect, single vector having the same effect, having the same effect as two or more vectors acting together. Effect as two or more vectors acting together. So now we're looking for something that is actually going to give us this answer. Therefore, they were having an option of 3 and 12. So 3 plus 12, they were going to get a value of what? Of 15, right? So 3 plus 12 is going to be what? A 15 there. Considering that we're assuming all these vectors are heading in the same what direction, right? So it means to the right is positive there. We're going to say 3 plus 12 is equivalent to, what? To 15 there. Then to put a hold, if again, let's say these two, they are actually opposing each other, the 3 is going this side and then the 12 is heading this side, right? So what are we going to have as our resultant? If we're choosing to the right as positive, it means you're going to say 12 minus 3, which is going to give you a value of what? Of 9 there. So we do not have 9 there. So the maximum value that we can get there is 15, and the minimum value there that we can get is maybe minus 3 plus 12, which is equivalent to minus 9. So those are the values that we actually can get from these two vectors. Therefore, all these other ones are actually going to be what? To be incorrect. So the only correct option there is actually 15. Remember, we got it from a definition of a resultant, which is a single vector having the same effect as two or more vectors acting together. Then we proceed to question 1.4. 1.4, they were given a question that reads, a car is traveling at a constant velocity. So the velocity is constant there along a straight road. It then slows down. There is slowed down uniformly in the original direction. So there is no change of direction there. Which one of the following velocity time graphs? So we're given velocity time graphs represents the motion of the car. So we need a constant velocity, right? So a constant velocity, the one that we're actually going to have there is the one that does not change, right? So if we can look at option A there, right? So the first one, that is A there, we're assuming, let's say, a value of 0, then 10, 20. Can you see this actually graph shows that the velocity is not constant, it's actually what's increasing. So our option A is going to be incorrect, right? Then after that, we're also having option B. So the first part there is actually what, assuming, let's say, 10 again there. So the first part there, you can see that the velocity is what is constant. We're having a constant velocity, but after that, it no longer decreases, it's actually what's increasing. But here we need something that actually slows down after that constant velocity. So our option B is also going to be what, incorrect. So let's look at option C there. The first part there is constant velocity. So V is actually constant. V is equivalent to what, to constant there, right? Then after that, what happens? We can see our velocity is now what, decreasing, because it's heading towards 0. So our correct option there is going to be option C. Then, however, option D is incorrect, because now we are moving only at a constant, what constant? This is constant velocity. So the final part there, it doesn't actually represent the final part where this actually car is slowing down uniformly. Then we're going to proceed to question 1.5. So 1.5, it reads, in the equation delta x is equivalent to vi delta t plus half a delta t squared. The part that of vi delta t represents what? So basically here we're actually representing displacement, but how do we actually like work this one out? Remember, we know velocity is actually defined as the rate of change of displacement, right? So velocity is the rate of change, rate of or change of displacement, rate of change of displacement, right? That's our velocity there, right? So placement, okay, so it means by formula, I'm going to say V is equivalent to delta X all over delta T, right? So back to this triangle that we usually use there, if I can draw it like that there, then allow me to change color there so that we can represent these values, right? So at the top there, we're actually going to have my delta x there, which is my displacement. So delta x there, then my velocity as well as my delta t, right? So here, what we are given here is vi delta t. So it means here, if we were to manipulate this one to get the top part, which is our displacement there, we are supposed to multiply v and delta t. Take note, the I there is just for initial velocity, but here the measure thing that we are referring to is our velocity. Therefore, here, that's why we are saying the answer is going to be our displacement there. So the correct answer is going to be our option D, which reads displacement there. Then we're actually going to proceed to question 1.6. So this is the correct answer. All these ones are incorrect. Then we proceed to the question 1.6, which reads there. A car is traveling at a speed of 25 meters per second on a straight road. What will be the speed of the car in kilometers per hour? So here, basically, what they are trying to tell us is to convert 25 meters per second to kilometers per hour. Therefore, for us to convert this one, we're going to say, take that value of 25 and then just multiply it by 3,6, right? So multiply 25 by 3,6, and then you're actually going to get a value of what? 90. So that value now is in what? Kilometers per hour. So our answer there is going to be our option B, which is 90 kilometers per hour. The rest are actually what? Incorrect then. Then we proceed to question number 1.7, which reads, which one of the following can be used to calculate velocity? So we're looking for something that can be used to calculate velocity from a displacement, position, or position versus time graph, right? So this is what we're having here. So I'll just like write it here. So it means here I can say this is my time in what? In seconds. Then here I'm going to have my displacement. So displacement or position, right? So here is usually not in meters, right? So now we are asked here, which one of the following can be used to calculate the velocity from a displacement time graph, right? So this is what we are having there. So in terms of this, we are actually going to say the gradient of the line. So let's say this is the origin 0, then our displacement is actually increasing like that along the time, right? So we're actually going to have the gradient of the line, which is what the graph there. So according to this there, if I can just like change here, I'm going to say there, like that dotted line there, right? So and again a dotted line here. So here is same as what the gradient. So this is the change in what's in x, which is your displacement, right? All over change in what in time. Therefore, remember the equation for velocity. How to calculate your velocity? Velocity is what? Change in displacement over change in time. So according to that, we are using the gradient. From math, the gradient, remember, is equivalent to change in y all over change in what in x. So in this case, your x there represents what? Your displacement, which is your vertical axis, and then or your y-axis. Then your change in time is your y-axis. Therefore, it means the gradient of the line is actually going to give us a value for velocity. So here for area under the graph, this one is incorrect, and then this one is incorrect also, and that option is also incorrect. So that's our multiple choice questions. As we proceed to the last one, which is 1,8 there. So we are asked about the SI unit of what? Acceleration, the units of measurement for acceleration. So the units of measurement for acceleration is meters per square second. So our correct option there is going to be what? To be A. Take note of B there. B there is no per second there. So there is a missing thing at the top per second there. Then option C here is meters per second, which either can refer to velocity or speed, right? And then the last one there, which is meters second, right? So like that is not per second. It means there is no rate there, or there is no division by what by time there. So also this one is incorrect. So our correct option there is going to be our option A, like that. So which is meters per square second. Always take note of that unit of measurement. Then we proceed to question 2.1, which reads there: a certain organic acid has the following composition, which is 54.55% of carbon, and then 9.09% hydrogen, and 36.06% oxygen. Then the molar mass of the this acid was determined to be 88.88 grams per mole. Therefore, the first part there, we are asked to define the term empirical formula. So to define empirical formula, we are going to say this is the simplest whole number ratio. This is the simplest whole number ratio, simplest whole number ratio, whole number ratio, number ratio, simplest whole number ratio of atoms in a compound, of atoms in a compound, atoms in a compound, like that. Okay, so this is what we are having in terms of our empirical formula there. Okay, so mm, okay, then 2.1.2, they determine the empirical formula of the organic what compound, right? So for us to determine the empirical formula of this organic compound, we're going to like draw a table easily like this, right? So we're going to start with our carbon, then we're having our hydrogen, and then the last one is our oxygen, right? So now this is the table that we're actually going to manipulate when you're calculating our empirical formula. So allow me to just like divide it like that, right? So now we're going to take the percentages as they are given, right? So the percentage there for carbon were given as 54.55. So there I'm going to say 54.55, 54 comma 55, right? And then the one for hydrogen is given as 9.09. So for hydrogen is going to be 9.09, and then the last one for oxygen there were given as 36.36%, right? So it's going to be 36 comma 36, like that, right? So this is what we're having here. So here I'm going to say number of mole is equivalent to m all over m. So the first step there, we are supposed to calculate the number of moles, right? So according to this, let's refer to our periodic table. Remember, we said our carbon there is carbon 12, right? So it means we're going to divide by 12 there. I'm going to say carbon divided by 12. Then my hydrogen there has got a relative atomic mass of 1 there, and then oxygen is actually what, our 16 there. So for oxygen, you can see we're having a value of what, of 16 there, right? So it's 1 and it's 16. Therefore, I'm going to divide this one by 1 and then divide this one by 16, all over 16, right? So if we were to do our math there, 54.55 divided by 12, we're going to get a value of 4, 5458 moles, right? 58 moles, right? Okay, so these are the moles that I'm going to get there. So any number you divide by 1, it retains its value, and then 36.36 divided by 16, I'm going to get a value of 2,2,725, right? So this is what I'm actually having there. So if I'm having that like that, so these are my number of what, of moles, right? Then after that, now I'm supposed to check on the ratio, right? So the mole ratio there, right? So now the simplest ratio that I'm actually going to get there is to divide by the least number of what, of moles, right? So the least number of moles you can see is 2,2725. Therefore, I'm going to say 4,5458 all over 2,2725, right, is equivalent the 9,09 all over again 2.2725, and then the last one there is going to be 2,2725, right, all over 2,2725, right? So now what we are going to have there is that this one is going to retain the same value there, right? So it's going to retain the same value, right? Okay, so that divided by the 2.27, 5 divided by 2.275, 2725, we're going to get a value of 1. And then if we say 9.09 divided by 2.2725, we're going to get a value of what, of 4, right? So then after that, we are also going to divide 458 divided by 2,2725, we're going to get a value of what, of 2, right? Then after this, now we're supposed to now write the empirical formula, right? So according to this day, we're going to have the empirical formula of what carbon there is, how many carbons, we're having 2 carbons, then there, according to that, we're having 4 hydrogens and then an oxygen, right? So this is how we're supposed to calculate our empirical formula for the organic what, acid there. So then to proceed there, it says here underneath that a sample of copper sulfate, then NH2O, right? So there is water of crystallization, is a mass of 7.49 grams. Then upon heating the sample, the mass of copper sulfate after all the water had evaporated was 4.79, right? So now we're asked to determine the value of N. So we're looking for the value of N, this N there at the top there, this N there at the top there, right? In the formula of this what, of this sample. Therefore, now I'm going to start with the mass of copper. So the mass of copper there, we now know is what, 4.79, right? So I'm going to say there, allow me to underline that one. I'm going to say the mass of copper. I'll start with the mass of copper sulfate. Mass of CuSO4 is equivalent to, according to this, we're given a value of what, 4.79 grams, right? I'm going to say this is equivalent to 4.79 grams, right? Then after that, now I'm going to say the mass of what, the unknown, the mass of what, of NH2O, right, is equivalent to, remember, it actually evaporated, right? So water evaporated the original copper sulfate with water there, it was 7.4, now 9 without water is now what, 4.79. So it means the difference is the water that actually what, evaporated there, right? So I'm going to say 7.49 there minus 4.79, like that, right? So now the mass of this is actually going to be what, 2.7 grams, 2.7 grams. So 2.7 grams. So this is the mass of water that we're actually having. Then after that, now we're going to retain the formula. Number of moles is equivalent to M all over m, right? So if you can look here, we are looking for this n, right? So this n there is more of like the number of what of moles there. Therefore, to proceed there, so is equivalent to, if I can start with the number of moles maybe of copper, they allow me to do it like this, number of moles of what of copper, I can just say bracket there, a number of moles of CuSO4 is equivalent to m all over m, like that, right? So this is equivalent to, if you're having the mass, so the mass that is actually given for this copper there with copper sulfate is 4,79, so it's 4,79, right, all over the molar mass of this copper, right? So we're supposed to refer to the periodic table to find our copper. Therefore it means here I'm having a 63.5 for copper, so I'm going to say 63.5, 63,5, then bracket there, because it's multiplied by 1, right? I'm going to say plus, then the sulfur there, sulfur is to be 32. If you look at sulfur there, we're having a mass of what? Of 32. So my sulfur is going to be 32 plus 32. Then I'm going to say plus again our oxygen there, right? We can see we're having how many oxygens? 4 of them, right? So again, there we're having our oxygen, which is 16, right? So therefore, I'm going to say bracket 16 multiplied by what? By 4, right? So if we were to do our math there, this is the same as allow me to scroll there. This is the same as 4,79 all over the value of 159,5, 159,5, right? So if we were to do our math there, 4,7 divided by 159,5, we're actually going to get a value of what? 0,03, 0,03, right? So it's more of like following the same procedure when it comes to what? To the empirical formula. But now we're actually going to also calculate the number of moles of what? Of H2O, right? So which is our water there is equivalent to m all over m, right? A mass over the molar mass, right? So the mass that is given for water there is 2,7, right? So I'm going to say 2,7 all over the molar mass of H2O. So to start with hydrogen, has got a relative atomic mass of 1, right? I'm going to say 1 multiplied by 2 because we're having 2 hydrogens. Then I'm going to say plus, then our oxygen we already know, just to confirm there, is 16, right? So I'm going to say plus 16. So this is same as 2,7 all over 18, like that, right? Then I'm going to get a value of what? 0,15 if I divide the 0,15, right? So now the next step that we are supposed to do is to divide by the least number. So to compare 0,03 with 0,15, it means my least number is going to be what? 0,03, right? All over this side, 0,03, right? So to divide a number by itself, you are going to get a value of 1. Then if I say 0.15 divided by 0,03, I'm going to get a value of what? Of 5. Therefore, it means my n, I can conclude the n is equivalent to what? To 5 there, right? So this is the 5 that I was looking for at the end there. So that's how we actually like go about it. Then we proceed to the next question, which is our question number 2.3. It says here potassium carbonate, right? Potassium carbonate reacts with excess HCl, which is your hydrochloric acid there, to form potassium chloride, right? Water and carbon dioxide. So these are our products, the water and carbon dioxide, which is a gas. In one such reaction, 115 grams of what potassium carbonate, which is K2CO3, reacts with excess HCl to the complete balance, to the complete balanced reaction given below. So it means here we are actually given a what? A balanced equation there. Then the first question there is we are supposed to define 1 mole of a substance, right? So 1 mole of a substance, right? So let's define 1 mole of a substance. We're going to say it is the amount of substance having the same number of particles as their atoms in the 12 grams of what? Carbon 12. So here I'm going to say it is the amount of substance. It is the amount of substance. It is the amount of substance there. Okay. So having the same number, having the same number of particles is they are is they are atoms they are atoms in 12 grams of carbon 12, right? So this is how we actually define our 1 mole of a substance. So please do take note, the importance of these are definitions, right? You refer to your exam guide for these definitions so that you can get 2 marks. Remember, there's no partial marks when it comes to definition of terms, right? Then to proceed to the next question, it reads here, calculate the number of moles of what? K2CO3, right? So the number of moles by formula there, we know the number of moles. How to calculate the number of moles? Okay, just to refer to your data sheet there real quick. Let me scroll up there, up there, up there, up there, up there. Right, so we're having the number of moles. Let me just rotate one more time, rotate, rotate, like that, right? So we're looking at the number of moles, the formula for the number of moles, right? So the formula is the number of moles is equivalent to M all over M. Therefore, I'm going to say my number of moles there. So number of moles there, okay, of what? We're looking for the number of moles of K2CO3. Therefore, I'm going to say number of moles of K2CO3 is equivalent to the mass all over the molar mass, right? So in terms of this, the mass that is actually given there for this one there is 15. Can you see there is given, this is 15 grams of what? Of K2, right? So K2CO3, therefore I'm going to say 15 there. So it's going to be 15 all over the molar mass, right? So remember, we're supposed to use our periodic table when it comes to this one. Then to scroll down there to look for potassium there, just to rotate there. So our K there you can see is 39, right? So I'm going to say 39 multiplied by 1, it will return 39. Oh, there are two of them, right? So it's more of like 39 times 2 there. 39 multiplied by 2. Then I'm going to say plus. Then the next one is carbon, which is our carbon 12. Just to confirm for you there, this is the value that we're looking for. The relative atomic mass there, which is 12. Then I'm going to say 12. Then I'm going to say plus because I'm multiplying by 1 there, just like right 12. Then our oxygen is 16 times 3, right? Therefore, what we are going to get there at the bottom is more of saying 15 all over 138, which is 138. Therefore, what you are actually going to get there is the number of moles, right? So this is equivalent to 0.1087 moles, right? So if we were to round it off there, we're going to get a value of 0.11 moles, right? Is our final answer like that. So this is how we actually attempt our question 2.3.2, right? To proceed to question 2.3, 2.3.3, it says determine the volume of what? Of carbon dioxide at STP, right? So standard temperature and pressure, right? So we're looking for the volume of carbon dioxide, right? So in terms of this day, we are supposed to use the mole ratio between our carbon dioxide as well as our K2CO3, right? The mole ratio between this and that one there, right? So I'm going to say the mole ratio between this one, I'm going to say K2CO3, allow me to underline there. I'm going to say K2CO3 versus our carbon dioxide, right? CO2, like that. Okay, so now to check the balanced equation, according to this, this is 1:1, right? So the mole ratio there in terms of our reaction there is 1:1, right? So it means the number of moles I'm going to use for K2 is the same number of moles that I'm actually going to use for what? For carbon dioxide, right? So it means here I'm going to have a value of 0.11, and then this side also I'm going to have a value of 0.11. Why is that so? Is because according to the mole ratio, these are actually what? Equal. Then after that, I'm going to say the number of moles of what? Of carbon dioxide there, right? CO2, right? So remember, this is a gas, right? So I'm going to say V all over VM, right? So just to confirm with the data sheet there, so where you find this formula, it says the okay, there it is there. So N is equivalent to V all over Vm, right? So this is the formula that you're actually going to manipulate. So the number of moles there, we're actually going to have that one. Then after that, according to this, the number of moles that we are having for carbon dioxide there is 0.11. So I'm going to say 0.11 is equivalent to the volume that we're looking for. So the Vm there is a standard. Therefore, because it's standard there, we should be given it as a standard since we are told it's at what? STP, right? So if I can just like scroll a bit it there, right? So you will see that what we are having here is the molar gas volume, right, at STP, and then this the VM, and then the value there is 22,4. So therefore I'm going to divide by what? 22,4. So it's 22,4. Therefore, if I divide that, I'm supposed to cross multiply. Therefore, my V, to make V the substitute formula, I'm going to say V is equivalent to, I'm supposed to cross multiply that one, 0,11 multiplied by 22,4, right? So my final answer there is I'm going to get a value of what? 2,46. So 2,46, and then the units of measurement, remember they are in what? dm cubed. Then that's how we attempt our question there for 2.3.3. Then we're going to proceed to question 2.3.4 there, which reads, after the experiment was performed, it was found that 14,5 grams of the KCl was actually formed, right? Then calculate the percentage yield. We are looking for the percentage yield of the reaction, right? So how do we go ahead and calculate percentage yield? Allow me again to underline that one there to show demarcation between these two, right? So now, if we're having this one there, we're actually going to say, according to the mole ratio again, we're actually going to compare K2CO3, okay, versus there, which one do we actually have there? The percentage of what? KCl, right? So we're going to go back to our balanced equation to look at KCl. So can you see here, the mole ratio here, it says here, according to this K2CO3 potassium carbonate is actually 1, and then the potassium chloride is, I mean, is 2. So the mole ratio there, it means is 1 is to 2, right? So I'm going to say KCl on this side, right? So the mole ratio again here is 1 is to 2, right? So why are we using K2CO3, which is our potassium carbonate? Because there we have the number of moles of this what? Potassium carbonate, right? So it means now, according to our calculations, we said these ones is 0,11, right? So is 2. So what does that mean? If I'm having 1 this side, I'm having 2 this side, it means I'm supposed to double this one. So mathematically, if I'm going to put an arrow there, I'm going to say this is same as 2 over 1 multiplied by 0,11, right? So it is actually going to give me a double value, which is equivalent to 0,22 moles, right? 0,22 moles, like that. Okay, then to proceed, these are the number of moles that we are having for KCl, right? Then after that, I can say now the number of moles of KCl, right, for us to calculate our mass there, right, is equivalent to m all over m, like that, right? So the number of moles I already have there, which is 0,22. Therefore I'm going to say 0,22 is equivalent to the mass that we're looking for all over m there, right? So the m, the molar mass of KCl, we're going to refer to the periodic table real quick there. So the molar mass for potassium there, K is, I mean, is 39 there. You can see it's 39. And then chlorine there, Cl, which is our chlorine there, is going to be our what? Our 35.5, right? So we're going to say KCl there, we're going to have a value of what? K is 39, right? And then plus there 35.5, right? 35,5, right? So mathematically there, if we were to do our math and cross multiply there, therefore I can just say 0,22 is equivalent to m all over, if I add these two, they're actually going to give me a value of 74,5, right? Therefore, for me to get the value of m, I should say m is equivalent, and then cross multiply 0,22 multiplied by 74,5, right? So if I'm to do my math there, I'm going to get a value of what? 0,22 times 74,5 is a value of 16,39 grams, right? So these are the grams that I'm actually going to have there. After that, now I'm supposed to calculate my percentage yield. Allow me to use that small space there. So percentage yield there is equivalent to, so percentage yield is equivalent to, so if I can say percentage yield is equivalent to, so it's going to be the actual yield all over the theoretical yield. Actual yield, okay, all over the theoretical yield, okay, then we multiply that by 100, right? So as a percentage, right? Remember, we're trying to get this as a percentage, and then this is equivalent to, so the mass that you actually got there, it was, I mean, it's 14,5, 14,5, so 14,5, just to look at it there. So we're having our, okay, so I'm going to say 14,5 determine the just scroll a bit there, right? To show you where I get my 14,5. Okay, so this is the mass that we are actually given. There is 14,5, right? After the experiment was performed, it was found out that 14,5. So this is the actual yield that we're actually having there, which is 14,5 all over the theoretical yield, right? So the theoretical yield that we calculated there, we were expecting to get this one in theory. Therefore, it's going to be 16,39 then multiplied by 100, right? So that we can convert this one as a percentage. If we were to do our math there, we're going to get a value of 88,47, 88,47% like that. Okay, so that's our what? Our theoretical yield. Okay, the yield, the percentage yield that we're actually looking for. So with that being said, we are done with question 2.3.4. Then we're going to proceed to question 3 now, which is the physics part, right? So question 3, there is two donkeys are pulling a cart, right? One of the donkeys pulls the cart with a force of 100 newtons and the other donkey pulls with 80 newtons, right? Both forces act horizontally to the right, so we're given direction there. So the cart experiences a constant force of 40 newtons in the opposite what direction? Then the mass of the cart is given as 50 kg. Then the first question there says define the term resultant vector. So this one, remember, we already defined it. We said this is a single vector that has got the same effect as a single vector having the same effect, having the same effect as two or more vectors acting together. Vectors acting together. So this is what we are having there in terms of our what? Our definition for a resultant vector. Then to proceed to question 3.2, 3.2 reads with the aid of a vector diagram. So they're asking for a vector diagram. Determine the resultant force on the cart, right? Use a scale of 1 centimeter is to 10 newtons, right? So it means 1 centimeter is equivalent to 10 newtons, right? And then we're supposed to determine the resultant force there, right? So it means here, let's just like deduce the information that we're given there. We're given a value there at the top of what? Of 100 newtons, right? So it's going, pulling this donkey is going to pull at 100 newtons to which direction? To the right, right? So I'm going to have a force going to this side, which is, 100 newtons there. 100 newtons, and then another one also we're told is pulling at what? 80 newtons, and then they are pulled both sides what? To the right, right? Okay, so I'm going to have a value of how many? Of 80 newtons there, right? Then after that, now I'm also told that the cart experiences a constant of what? 40 newtons in the opposite what direction? So it means this one is heading this direction backwards, right? So I'm going to have a value of what? Of 40 there, right? So this is 40 newtons, right? Then after that, now I'm asked to determine my resultant, right? So generally, if we're to determine our resultant there, we're going to choose a direction, maybe say to the right as being what? Positive, right? So it means everything that is going to the right has to be positive. Therefore, what does that mean? It means I'm going to have a value of 100 being positive, then plus 80, which is positive, but my 40 is heading in the opposite direction. So I'm supposed to subtract that one. Therefore, at the end of the day, I'm going to get a value of what? 120 newtons, 140, sorry. 140 newtons. So that's my resultant. Therefore, where is it going there? To the right, right? Because it's a positive value. Therefore, this arrow has to go in this direction, heading to to the right there, right? So according to this, they are saying 1 centimeter to represent 10 newtons, right? What does that mean? It means that if I can just like indicate there at the bottom, so it means my 100 newton force there should be equivalent to 100 newton force there should be equivalent to 10 centimeters. Let me just say equal there 10 centimeters, and then my 80 newtons there should be equivalent to in length to 8 centimeters, 8 centimeters. And then after that, this is 140. Sorry, I forgot to write 140 in newtons there. Then we also have this one, which is 40 newtons there. So to the left, there is 40 newtons, which is equivalent to 4 centimeters. And then the resultant there, we got a value of 140 newtons. Therefore, it means our line has to be 14 centimeters according to the scale that says 1 centimeter is to 1 centimeter is to how many newtons? Is to 10 newtons, like that, right? So this is what you're going to have there in terms of this, right? Then to proceed there to the next question there. So the next question there reads, uh, is the mass of the trolley a scalar or a vector quantity? So our correct answer there is a vector, is a scalar quantity. So mass is a scalar quantity. The correct answer is going to be a scalar quantity. Our mass is a scalar quantity. While on the other end, remember we're going to have our weight. Our weight is going to be a vector quantity. Then we're actually going to proceed to the next question, which is question 4. So question 4, still physics there. It reads, Buffalo City Metro boys under 15 rugby team are having a training session along a beach in a straight line. Sections of the distance traveled while they train are shown in the diagram below. Then we are asked to define the term distance, right? So distance there, by definition, is the total path length traveled, right? So it's defined as the total path length, total path length traveled, like that, right? So this is how we define our distance, right? Then after that, then they are asking us to determine Sineless average speed, right? So average speed, okay, we're told if he jogs from B to D, right, and then back to A, right, in 60 seconds. So we're given time. So he starts jogging from what? From B until he gets to this point of what? Of D there, right? So then after that, we're told also his jogs are back to what? To the starting point, which is a total distance of what? Of I mean there. Let's see. So from there, he jogs back to the starting point, which is our what? Our A there, right? So now we are supposed to calculate the average speed, right? So average speed, remember, we're going to say our average speed. The first thing that we need to know in terms of this, we need to get the total what? Distance, right? So total distance there, that was actually traveled by Sanele is equivalent to, so he moved from B to C. So he moved from B to C there, right? So if he moved from B to C, from this part to this part, it means he traveled a distance of, I mean, of 50 meters. So I'm going to say 50 plus, then after that, he traveled from C to this point, which is D. Therefore, I'm going to say plus my 20 there. Then after that, now we know he also traveled from D to C. He passed C. So I'm supposed to add that 20 there. Then after C there, he also traveled until point B, which is, I mean, meters, which is a 50. Then after that, he also traveled a distance of, I mean, from B to A, which is 30, right? So if I do my math correctly, there is 50 and then plus 50, which is a total of what? 100 there. Then after that, I'm going to have a 30 plus 20, which is 50. So I'm going to get a total distance of what? 170 meters, right? Then after that, by formula there, your average speed, right? Average speed is equivalent to the total distance traveled. So total distance all over the time, right? So total time, right? So total time, like that. Okay, so what does that mean? This is same as is equivalent to, so my total distance there, we already calculated it, total distance of what? 170, then divided by the time which it took there. It took, I mean, seconds, 60. Therefore, if I'm to do my math there, 170 divided by 60, I'm going to get a value of 2,83. Therefore, because the units of measurement is going to be 2,83 meters per second, right? That's how we actually calculate our distance. Remember our average speeds. Remember, speed is a vector quantity. That's why even if I'm going back to A, I still add using what? A positive value, because distance is a scalar quantity. It doesn't require what? Direction. Then after that, now I'm asked to find the term velocity, right? So how do we define velocity, right? So it means velocity is defined as the rate of change of what? Of displacement, right? So we define velocity as the rate of change of displacement, right? So rate of change of displacement. Okay, so that's how we actually define our velocity. Then we're actually going to proceed to 4.4, right? So 4.4, the rates are 4.4 rates is calculate Sanel's average velocity in 4.2 above, right? So we're looking for average velocity, right? So in terms of the average velocity, what we're actually going to do is to say your average velocity. Remember, we're going to say your velocity there is equivalent to delta x all over change in time, right? So now let's look at our displacement there, which is delta x, right? So if we're having our delta x there, we're actually going to say this is equivalent to, if I say delta x is equivalent to, so my displacement there, where did Sanelli start, right? We're going to erase that one there. So I'm going to say going to the right there, which direction? Going towards D there is actually going to be what? To be positive, right? So I'm going to say in this direction, I'm going to consider it as being what? Positive. So this side as being what? Positive, right? So let's look at the distance that he actually traveled from B to D as being what? Positive, right? So this is the distance that he actually traveled. Therefore, I'm going to say 50 plus 20, which is 70, right? So I'm going to say 70, then plus, then after that now, what I'm going to say there in terms of the displacement there. So it means here, uh, from D to A there, from D to A is now the opposite what direction. Therefore, I'm going to say plus minus, right? So if we are to add our 20 plus our 30 there, I'm going to get a total distance of 50 and then plus 50, which is 100, right? So I'm going to say plus minus 100 there. Therefore, I'm going to say my answer there that I'm going to get a negative 30. So negative 30, what does that mean? Is heading in the opposite direction, right? So then after that now, I'm going to say 30 divided by 60. 30 divided by 60, I'm going to get a value of what? 30 divided by 60, I'm going to get a value of 0, 30 divided by 60, I'm going to get a value of 0, 0.5, right? So it means my velocity there is 0, 0.5 meters per second, right? So in terms of this, I'm going to say which direction there, left, because I was actually going to get a negative value. In terms of this, I was supposed to say negative 30, therefore I'm going to get a value of negative 0, 0.5 meters per second, right? So remember, we chose to the right as being positive. So it means now he's heading what? Left. That's why we are going to use that what? That value there. Then we proceed to the next question there, which is our question number 5. So question number 5 there is there. Question 5. To investigate the motion of a trolley, traveling at a uniform acceleration, right? A runway is set up as shown in the sketch below. Then the slope of the runway is adjusted before readings are taken, right? So now what we're actually going to have is this pulley there running up a ticker tape timer like that. Then we're also having our tape with what? With the marker then, right? So now can you see now they formulated an inclined plane there, right? So this is the horizontal part, and then we're having an angle there. So there is a theta there, angle theta. Then after that now we're asked to give a reason why the slope of the runway has to be adjusted, right? So now the reason why we adjust this slope to an inclined plane there is to compensate for friction, right? So we're going to say to compensate for friction, right? So this is what we're having there. So to compensate for friction there. Then after that now, the next question is there. The ticker tape is analyzed and the displacement, which is change in position, is measured after every 0.2 seconds. And then the table below shows the data that has been what? Obtained, right? So it means now measured after 0.2 seconds. Every 0.2 seconds we are measuring it, right? So now it says here for the investigation, write down the independent variable, right? According to this one, we are having our time there. So our time is always going to be the independent variable, right? So time is going to be our independent variable. So there I'm going to say time is my independent variable. Then after that, you are asked to refer to the dependent variable. So dependent variable, in terms of this, we are having our time as well as our what? Our position. So it means our dependent variable is going to be our position like that. Okay, then I'm going to proceed to the next question, which reads copy and complete the table above in your answer book, right? 3 marks there, right? So let's look there. We're looking for these 3 values, but here already we're told the ticker tape is analyzed and the displacement changes in position is measured every after 0.2 seconds. So it means I'm supposed to add 0.2 there. So 0 to 0.2. Then if I add again 0.2 on 0.4, it means I'm going to get a value of what? 0.6. Then if I say 0.8 plus uh 0, 2, I'm going to get a value of 1, right? I can just say 1, 0 like that, right? So those are the values that they're actually looking for. Then after that, now I was asked to draw a graph of position versus time for the motion using the values given from the completed table in 5.3. And then I'm asked to indicate, I'm asked to indicate a suitable heading. That's number one. I'm asked for the suitable heading, then correct labels in appropriate scale on both axes, then all points plotted correctly, right? Then I'm actually going to say, then after that, I'm going to just like refer to this there so that I can make use of the table that I'm looking for. Okay, it's at the bottom there. It's at the bottom there, right? So it's at the bottom there. Sorry about that. So I'm going to scroll down there. Allow me to quickly rotate this to that, right? Okay, so this is what we're having there is our table. Okay, so I'm going to use the graph paper there. Okay, allow me to just like minimize a bit so that it can fit the whole screen like that. Okay, so now I'm having which values there according to this there. Let me just like quickly go back to the table. So I'm having time versus what my position, right? So I'm going to write there time versus what position. Oh, is the other one, is the other one, is the other one. Okay, so I'm having my time here. So I'm going to say here I'm having my time in what in seconds. Then I'm going to say this side I'm going to have my position, right? Okay, so now suitable heading is actually position versus time graph, right? So this is the name of my graph, the position versus my time graph. Therefore, I'm going to have a plot there that is the origin, right? So let me look at the time that is actually given. So my time is from 0 until 1 second there, right? So I'm actually going to use a scale of what 0, 2. I'm going to start from 0 to 0, 2. So if I can say 0, 2 here, 0 0.2, 0 0.4, 0.6, 0.8, and then 1.0. Then after that, I'm going to have 10, 1 comma 1 2 like that, right? So it's actually going to increase going in that direction, right? Then my position there, I'm also having position there from 0 like that until 650, right? So exponent of what, of 3 there, right? So I'm going to say there, according to this graph there, I'm going to say position, sorry, in meters, right? So if I'm having my meters, then I'm going to have my 0 there. And then if I can say 3, 0 0, 10, 20, 30, 10, 20, 30, 40, 50. Yeah, it's going to be enough. So here I'm going to say 0, 10, 0, 20, 0, 30, 0, 40, 0, 50, and then 0, 60, right? So check this one is actually what as what told you the value there is 10 exponent -3. So it's just like a conversion factor that I actually use there. So my 0 goes with 0, so it means my first point there is going to be there, right? Then after that, I'm going to have a value of what time. If time is 0, 2, my displacement there is 30. So if you divide there 30 multiplied by that, you're going to get a value of what 0, 0.03, if I'm not mistaken. Then we proceed there. It means 0, 0.1, 0, 0.2, 0, 0.03, right? So 0, 0.03 is below this one, right? So I'm going to count there 1, 2, 3, right? So I'm going to say 0, 0.1, 0, 0.2, 0, 0.3, right? So it means my first point is going to be there. Then after 0, 0.4 seconds, according to this, where are they? They are exactly at 0, 0.2, right? So 0, 0.2, then 0, 0.2, there 0, 0.2. So where is my 0, 0.2? So my 0, 0.2 is somewhere there, 0, 0.20. Then after that, what am I having? I'm having a time of 0, 0.4. It's 90. Oh, sorry, it says 30 there, right? So 0, 0, 30, and then at 0, 0.4, I'm at 90. 0, 0.4, I'm at 90. So 0, 0.4, I'm at 90. Let me erase that one. So which is more of like 0, 0.9, right? So it means my 0, 0.9 is going to be somewhere then. Then after that, now I'm going to say my 0, 0.6 goes with what? With 200. So if I say 200 there, what am I going to get? 200 times 10. So 200 times 10 exponent -3. So it's more of like 0, 0.0. 0, 2, like that. Okay, 1, 2, 3, 0, 2, right? So it means there I'm at 0, 2. So this means 0, there I'm going to plot with that one. Then 0, 8 there I'm going to plot with what? 0, 8. Where are we at 0, 8? After 0, 8, we're at 380 seconds, right? So 380, so it's more of like 38 there, so which is somewhere there. Then after that, we are going to have our last value, which is 1. After 1 there, second one is 650, which is more of like 65, right? So 1 there, 50, we've got our 60. So 1, 2, 3, 4, 5. We're somewhere then. Then after that, we are required to join these lines like that. So we're going to like join them nicely to formulate something like cumulative or jive or give cave like that, right? So this is what you're going to have there in terms of our graph, right? So then to look at the plots that were actually being asked there, we just like check there. All points are plotted, yes. Appropriate scale on both axes, yes. Then correct labels on both axes, yes. And then a suitable heading, we actually gave it a suitable what heading. Then to proceed there to question number 6. Question number 6 reads there, the velocity time graph shown below was obtained for a car accelerating on a horizontal track in the southerly direction, right? So it's heading towards the south, this car. Then after that, describe the motion in ways, describe in ways the motion of the car at section CT. So let's look at CT there, right? So between C and T there, between this point C and what? And T, right? So you can see there, we are moving at a constant velocity. So between C and T, I can say C and T, C, T there, right? So it's moving, the car travels at a constant, car moves at a constant velocity, then I can add the time for how many seconds. So from 20 to 40 seconds is constant velocity. So I'm going to say the difference there is going to be our main constant velocity of what, let me just specify there, of 16 meters per second for how many seconds? For 20 seconds, like that. Then I'll ask after that, I'm asked in terms of what? DE, right? So D to E, I'm going to say DE there. So what happens there in terms of DE is that the velocity of the car decreases. The velocity of the car decreases. Okay, so it decreases. They are from what? From 16 there. Decreases from 16 meters per second to what? To 0, right? So to 0 meters per second, which is at E there, to 0 meters per second, right? So how much time did it take there? From 40 to 60, the difference is going to be what? How many seconds is actually going to be 40 to 60 is 20 seconds, right? For or in what? In 20 seconds, like that. So this is the motion. That's how actually what we describe that part there, right? So then to proceed there to question 6.4, 6.2 reads, without using equations of motion, right? Calculate the acceleration of the car during the first 10 seconds, right? So we're looking for the first 10 seconds, right? Which is this part there, right? So remember, if we're calculating our acceleration there, we're going to say your acceleration is equivalent to delta V all over delta T. Remember, it's defined as the rate of change of what? Of velocity. Therefore, this is same as Vf minus Vi all over change in time, right? So this is also the same as, now let's substitute the values that we are having there. So at B there, the final velocity, that's our final velocity, minus the initial, we started at 0 all over the time that is actually taken there. It took us how many seconds? 10, right? So if we were to do our math, 12 divided by 10, we're going to get a value of what? 1,2. Then I'm going to say meters per square second. Then remember, he was heading in which direction? To the south. Therefore, I'm going to say south, like that. Okay. So then to proceed to 6,2,2, it says calculate the displacement of the car for the entire 60 seconds, right? So for this entire 60 seconds, we are actually going to say your displacement there is area under the graph, area under the graph, area under the graph, like that, right? So if we're having something like this, to quickly work it out, do I have enough space here? No, 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 no. So I'm going to like divide it into, I mean, parts 1, 2, 3, 4. So I'm going to say 1, 2, 3, 4 parts, right? Okay. So to make it easy, let me just manipulate this other space here. I'm going to start by saying from 0 to 10, right? So 0 to 10 seconds there. So we've got our part there that is 0 to to 10 like that, right? So if I'm having something like that, then I'm actually going to proceed to the next one that is actually going to be from B to C. So from B to C, there is 10 to 20. Therefore, I'm going to say 10 to 20 like that. After that, now I'm going to say the third one is from C to D, which is 20 to 40. So it's 20 to 40. So I'm going to have 20 to 40, 20 to 40 like that. And then the other one there, which is now from D to E, is actually going to be from 40 to 60. Therefore, I'm going to say 40 to 60 as my final 40 to 60 like that, right? So then after that, I'm supposed to add all these, right? So for me to add all these, I'm actually going to say from 0 to 10 there, I'm actually going to say what type of shape do I have there from 0 to 10, right? So you can see this is a triangle there. If I'm supposed to say half base times height, right? I'm going to say the area there is actually going to be, for the first part is half base times height, and then plus the second one there. So the second shape that I'm actually going to have there is more of like, this is a trapezium. Therefore, for a trapezium, I'm going to say half base, sorry, not half base there. I'm supposed to say half of A, so half bracket of A plus B, and then multiplied by the height, right? And then I'm going to add again from 30, 20 to 40 there, 20 to 40. What we have is a rectangle. Therefore, I'm going to say L multiplied by B, and then the last one there plus the final part there is a triangle again. Therefore, I'm supposed to say plus half base times my height. That, so according to this, my half, the base of this one there is 10, right? So from A there, from 0 to 10, my base is going to be 10, then half multiplied by 10, then multiplied by the height. So the height there is from this start there until the top. So where are we? We're at 12 meters per second. Therefore, I'm going to say multiplied by 12, then plus again half. So A there, according to this, these are the parallel sides, right? So this side is parallel to this side, right? So these two sides are actually parallel. So one of them is going to be A, and I'm choosing this one to be A, and then B, and then my H is going to be that height there at the bottom there, right? So it means my A there is going to be having a value of 12. Therefore, I'm going to say 12, and then plus my B there, I'm going to have a value of what? Of 16. At the top there is going to be 16. Therefore, I'm going to say 16 plus the base, right? For us to find the value of this base there, we're going to say the final, which is 20, minus the initial, which is 10. We're going to get a value of what? Of 10, right? Therefore, I'm going to say there are 10 here. So multiplied by 10, then plus, then for the rectangle there, I'm having this 20 there, this 16 there as the height. And then the difference from 20 to 40 is going to be what? To be 20. Therefore, it's more of saying me saying the value of what? 20 okay, it's 20, then multiplied by what? 16. 20 multiplied by 16 there, right? So 20 multiplied by 16, okay, multiplied by 16. And then the final one, I'm going to say half, and then the base there, what's my base there? From 40 to 60 is still 20. So I'm going to say 20, and then my height, where did we start from there? We started from a value of what? Of 16. Therefore, I'm going to say 16. Then after that, you're supposed to do our math, right? So according to my calculations there, if I do that, I'm going to get a value of 60, then say plus. If I do that one again, I'm going to get a value of 140, then plus again, I'm going to get a value of what? 20 times 16, which is 320, and then plus again the last one there, which is half of 20 is 10 multiplied by 60 is 16 is, I'm going to get a value of what? 160. Then I'm supposed to add that one. So the total displacement that I'm actually going to have is equivalent to 680 meters, right? So if I'm having 680 meters, I'm actually done with this part there. Then I'm actually going to proceed to question 6.3, right? So this is my question 6.3, right? So 6.3 reads there, sketch the corresponding acceleration versus time graph in your answer book for the first, what, 10 seconds, right? So for the first 10 seconds there, we actually calculated a value of what? Of 1,2 meters, what? Per square second there, right? So it means now, according to this, I'm actually going to say this is the graph there. I'm going to have my time in seconds. Therefore, I'm also going to have my acceleration, right, in what? In meters per square second, like that, right? So then after that, remember they were accelerating at a value of what? 1,2. So I'm going to have a value of 1, 2. For how many seconds there? It means for 10 seconds. Therefore, the time is going to be t. Then I proceed to the final question, which is question number 7. It says here, a car is traveling on a straight horizontal road at a constant velocity of 25 meters east, right? The speed limit along the section where the car is traveling is 100 kilometers per hour, and then use the calculations to determine whether the driver of should be fined for speeding, right? So we are supposed to convert. I'm actually going to convert this 100 kilometers per hour to meters per second, and then compare with it with 25, right? So for me to convert that one, I'm going to say 100 divided by 3,6, right? So I'm going to get a value of 27,78. So it's 27,78 meters per second, right? I'm going to get a value of that, right? So now this is what I'm actually having, right? Therefore, for me to compare, I'm actually going to say 25 meters per second is actually less than the one that is supposed to be traveling is 27,78 meters per second, right? So he is traveling at 25. It's a speeding zone of 27,78. So it means no, he shouldn't, right? So the answer there is no. So no, he shouldn't, because he's not speeding there. So shouldn't, like that. Then define the term acceleration, right? So acceleration is defined as the rate of change of velocity, rate of change of velocity like that, right? So that's how we actually go about that one. Then 7.3, what is the acceleration of the car at a constant velocity of 25 meters per second, right? So here is actually going to be 0 meters per square second. Why is that so? Because the velocity is constant, therefore it's not changing. Remember, your acceleration there is the rate of change of of velocity, and your velocity is not changing, therefore it means you are going to get a value of of 0. Then the next part, it is the driver of the car sees a pedestrian crossing which is 100 meters ahead and needs to come to a stop before the pedestrian crossing for pedestrians to cross, right? It takes 1 second for the driver to start applying his brakes, and a further 4 seconds, right? For him to come to a stop. Using your knowledge of physics, perform calculations to determine whether the car will stop before this pedestrian or not, right? So now we're having what we refer to the reaction time, right? So it takes to applying the brakes. So this is what we refer the reaction time, right? So the time you think of applying the brakes until you apply the brakes, that's what we refer to as our reaction time. Therefore, I'm going to say a delta x, which is your displacement. How much distance do you travel for the reaction time, right? For the reaction time, right? So how much distance did you travel before you started applying the brakes there, when you were thinking to apply the brakes, right? So mathematically, I'm going to say delta x is equivalent to vi delta t plus half a delta t squared, like that, right? So now, according to this, now the speed that the driver was traveling at there is given 25 meters per second, right? So I'm going to say there for the first second there is equivalent to 25, right? So now the time that it took for him is the reaction time there is 1 second, right? So I'm going to multiply by 1, then say plus half my acceleration there. So my acceleration, remember, is moving at a constant velocity, therefore it's going to be to be 0 there, then multiplied by 1, right? So this is my time, which is squared, right? So it means my delta x there, my delta x is equivalent to the value of if I do my math there, this is going to give me 0 there. For 25 multiplied by 1 is equivalent to 25. So it's 25 meters. Then also I need to calculate the delta x for the last 4 seconds, for the last 4 seconds there, for the last 4 seconds, like that. So then after that, I'm actually going to use an equation of delta x is equivalent to vf plus vi all over delta t all over 2, sorry, all over 2, then multiplied by my delta t all over 2, right? And then multiplied by my delta t, like that, right? So delta t, then what I'm actually going to get there is a value of so delta x is equivalent to, so it comes to a stop, therefore I'm going to say 0 there, final. Then initially you are traveling at 25, then for how many seconds then? For 2 seconds, right? So if we are to do our math there, I'm actually going to get a value of of 50. Therefore, now the total distance that I'm actually going to travel, so I'm going to say total distance there is equivalent to, I'm supposed to add 25 plus 50, therefore I'm going to get a value of 75 meters, right? After that, now I'm going to say 75 meters is actually less than the 100 meters there, right? So it means now how far was this pedestrian there? Pedestrian there was where? 100 meters. Therefore, what does that mean? It means there he stopped before, like the pedestrian crossing, right? So now the car will stop. As a conclusion there, we'll say the car will stop before the pedestrian stop, before the pedestrian crossing, like that. Okay, so that's how we actually attempt our paper there. So with that being said there, this is the end of our paper. Thank you. Hope you enjoyed the paper.